In segment 4.3, we'll talk about how to share and split keys. Up to now, we've talked about different ways of storing and managing the secret keys that control Bitcoins, but we've always put a key in a single place. Whether that's locked in a safe or in software or on paper, it's in one place. And storing the key in one place leaves us with a single point of failure, so that if something goes wrong with that single storage place, then we're in trouble. So here what we'd like to do now is be able to take a key and split it up into pieces and share those pieces around so that we avoid the single point of failure problem. And so we're going to introduce a cryptographic trick called secret sharing. The idea is we're going to take some secret, in our case a secret key, and we're going to divide it up into some number n of pieces. And we're going to do that in such a way that if we're given any k of those pieces, then we'll be able to reconstruct the original secret. But if we're given fewer than k pieces, then we won't be able to learn anything about the original secret. So for example, we might have n equals 2 and k equals 2. That means we're dividing the secret into two pieces, and you need both pieces to put them together. And a specific way of getting n equals 2, k equals 2 secret sharing like this is as illustrated here. That first we're going to generate a number p, which is a large prime number. It doesn't need to be secret or anything, just really big. S is going to be the secret, and the secret has to be between 0 and p minus 1 inclusive. And then we're going to generate a random value r secretly, which is also within the range between 0 and p minus 1. And now we're going to split our secret into two pieces, x1 and x2. Piece x1 is going to be s plus r modulo p. And remember that modulo is the operation that's sometimes written with the percent sign in programming languages. It just means take this value s plus r and divide it by p and keep the remainder when we do that division. That's s plus r modulo p. So that'll be x1, our first share. And the other share, x2, is going to be s plus 2r modulo p. Okay. And now if we have both of these shares, x1 and x2, we can combine them to reconstruct the secret s. What we do is we compute 2 times x1 minus x2 modulo p. So 2 times x1 is 2s plus 2r, and x2, which we're subtracting off, is s plus 2r. And so we have 2s minus s. That leaves us with an s. We have 2r minus 2r, and so the 2r's cancel out, and we're left just with s mod p, which is equal to s, because s is less than p. And so we can reconstruct the secret in this way. So given two shares, we can reconstruct. But given only one of the shares, it turns out we don't learn anything. And to see why that is, consider x1. We took s, which is the secret, but we added to it a random number, which could take on any value between 0 and p minus 1 with equal likelihood. And if you think about it, you can convince yourself that the result then of s plus r modulo p is equally likely to take on any value between 0 and p minus 1, and that's true regardless of what s was. And so this share by itself just looks like a purely random number and doesn't convey anything about what the value of s might have been. Similarly, this share by itself is also equally likely to take on any value between 0 and p minus 1, and therefore doesn't convey any information about s. So that's n equals 2, k equals 2. Given both shares, we can get back the secret. Given one share, we can't. Okay. Now in general, we can talk about how to get higher values of n and k. For example, let's talk about how to get higher values of n where k equals 2. That is, we're going to want to require two shares to be put together to reconstruct the secret, but we're going to make more than two shares that are eligible for use in this way. And so the way we'll do that is to draw our standard x and y axis here, and we're going to add a point here at 0, s, where s is the secret. And so obviously if somebody can learn what this point is, then they will have reconstructed the secret. Okay, now we're going to draw a line, and we're going to draw a line that has a random slope r. R is going to be generated randomly, and so we get a line like this. And now we can give out shares. The first share is this point here at x equals 1, and y is s plus r. The second share is here at x equals 2, and y turns out to be s plus 2r. The third share is here, x equals 3, and y is s plus 3r, and so on. We can go as far up this line as we want and generate as many shares as we want. Okay, now, if you think about it, you can convince yourself that given any 2 points, you can interpolate and find S, right? That's a property of a line. Given any 2 points on a line, you can interpolate the line. Imagine setting down a ruler that exactly touches, say, these 2 points, and then you can just draw a straight line along that ruler. So given any 2 points, you can reconstruct what this line is. You can see where the line crosses the y-axis. That will be 0, S, and that will give you back the secret. But given just 1 point, you don't really know anything. Because if you have, say, this point, well, the line might be sloped like this, but equally likely it might be sloped like this. It could be sloped any way at all. And so given just this point, you don't really know anything about where this line might cross the y-axis, so you don't know anything about S. And in fact, you can prove that if you do this arithmetic modulo a large prime p, like we did before in the previous slide, that in fact you can prove that any 2 points are sufficient to interpolate and find S, and fewer than 2 points don't tell you anything about S. And so this gives us n equals any value and k equals 2. All right, but now what if we wanted to require more than 2 points? Well, for 2 points we drew a line because any 2 points are sufficient to uniquely specify a line. If we want to require 3 points, what we're going to do is use a quadratic function because any 3 points are sufficient to reconstruct a quadratic function. And so we can use this table to understand what's going on. So if we use the equation s plus rx mod p with the random parameter r, that's the slope that we saw in the previous slide, then you need 2 points to recover s because you need 2 points to interpolate a line. If, on the other hand, if then you use a quadratic, that is s plus some random value r1 times x plus some other random value r2 times x squared, then there are 2 random parameters r1 and r2, and with any 3 points you can uniquely interpolate a quadratic and get back s. And we can just go up the ladder here. If we use a cubic function, there are 3 random parameters, we need 4 points. And in any case, you can generate as many points as you want on the line or the quadratic or the cubic. And therefore, you can get any value of n. And you see how you can get any value of k by just going to higher and higher order polynomials. And so this scheme will let you take any secret and split it into n shares such that k shares or more are needed to reconstruct. And that turns out to be a really useful thing because now you can take a secret key or other secret information and split it up in this way. Support k out of n splitting for any k and n. So let's talk about the good and bad that we get out of this process. The good part is that we can store the shares separately, and the adversary needs to be able to recover k shares in order to get back what the secret was. And that's a good news, right? That means that if we use, say, k equals 3, n equals 4, the adversary needs to break into 3 separate places. And if we're clever about storing those separate shares in places that are far apart and independently secured, then we can make the adversary's job much more difficult. And indeed, if we notice that the adversary has compromised one of those places, we can then race out and try to recover the other shares and address the problem. The other thing that's good about this is that we can afford to lose some of the shares. If we do 3 out of 4 secret splitting, then we can lose 1 share and we'll still have 3 left. And so we can put those 3 remaining ones together and still get back the key. So even though we're spreading out the information, there are more places where information might be lost. We can also tolerate the loss of some of those. In general, we can tolerate the loss of n minus k of them. Now that's the good news. The bad news is that if we take a key and we split it up in this way, and we then want to go back and use the key to sign something, we still need to bring the shares together and recalculate the initial secret in order to be able to sign with that key. And that point where we bring all the shares together and recombine them is still a single point of vulnerability where an adversary might be able to attack us. And that's the bad news. So although this is useful, it's not a panacea, and there's something else that we'd like, which is the ability to generate separate shares and use those shares separately in order to sign. And that's what's behind the concept of multisig that we saw earlier in Lecture 3. So if you recall multisig in Lecture 3, it lets you keep the shares or the different pieces that need to sign a particular transaction apart, and to allow them to approve the transaction separately without needing to reassemble the key at any point. So just as an example of application of that, suppose that Andrew, Arvind, Ed, and Joseph are co-workers. Let's say they're co-founders of a company, and the company has a lot of bitcoins. Hey, we can dream. Now, what we might want to do is use multisig to protect our large store of bitcoins. So what we're going to do is have each of the 4 of us generate a key pair, And we're going to, for our company's cold storage, store the coins so that we require multi-sig with 3 out of the 4 keys signing. Now the result of that is that we know that we're relatively secure if the 4 of us keep our keys separately and secure them differently, that someone would have to compromise 3 out of the 4 keys, that if some employee or even 2 employees go rogue, those rogue employees can't steal all of the company's coins because you would need a conspiracy of 3 out of 4 to do that. And we also know that if something goes wrong, if one of us loses our key, or if one of us gets run over by a bus and our brain wallet is lost, the others can still get the coins back and transfer them over to a new place. And so multi-sig allows you or helps you to manage large bodies of cold stored coins in a way that's relatively secure and that requires action by multiple people before anything drastic happens.